So, as we may already very familiar with, survey has been used as one of the main tools for understanding customers in trade in UK. And the majority of surveys use a traditional 5-point and 7-point scale, as it has the advantage of it is relatively easy to collect and analyze. However, it is also has a kind of disadvantage of it forces the participants to choose a single value, which sometimes may restrict their authentic expression. So for example, here is a question that think about if you are asked about your satisfaction with the cleanness of the toilet on the train. And we all know that it is very common that some people may visit the toilets multiple times during a single journey. And they may find, yeah, the first time it is pretty nice and clean, but the second time it's not really good. And so there is a mixed feeling of them towards a certain thing. And if we force them to choose a single value, then they may say, okay, then overall on average we choose neutral. But that does not really reflect their experience with somebody just have a neutral feeling of it. So more recently, in the field of computer science, that people have introduced an interval value scale. So instead of asking people to choose a single value, they are allowed now to choose a range to express their uncertainty around certain things. This kind of method has already been tested and used in quite a variety of fields like customer preference and cybersecurity. And we also developed a free software that enables the creation and administration of the interval surveys. So just to help you to understand how it works, here is a demo survey. And please give it a go by scanning it, and we will wait for a minute and a half before we continue. Well, thank you for trying. I hope it looks fun to you. And somebody will ask that how do we deal with or analyze this kind of data? So here is an example on the visualization. So we have the interval agreement approach, IAA, and it's just similar to work as a relative frequency histogram. So like the picture shows on top are 3 interval value data, and on the bottom is kind of showing for each rating what is the frequency of it. And also we have the measure of central tendency, like the interval average. It works quite similar to the average of the mathematical average. So instead of dealing with a single point data, we treat each interval as its lower bound and upper bound, and so we operate on that respectively. Try to use the interval value data in the railway customer satisfaction content. We combined it together with the very widely used Customer Satisfaction Index, CSI. And if you're not already familiar with it, and it is the idea is we collect the satisfaction and the importance score from the passengers or customers, and then we weight the satisfaction score by the importance score, and then we get the overall contribution. So for example, in the picture shows here, the attribute 3, we can say it gives the biggest contribution toward the overall satisfaction index. So we combine the interval data with this. And then we've worked on a study that overall have 160 participants that have traveled in UK by train in the last 7 days. And all those people are identified online, and the data was collected through Dexus, which is the software you just tried. And so we have 80 participants using the interval value scale, and 80 use the single point, which is traditional 5-point scale. And in this survey, we overall asked them about their satisfaction and importance of 14 different attributes that is adapted from the East Midlands Railway survey. So in that way, we can try to find out the things that those real stakeholders are interested about. So we have collected some demographic information to ensure between those two groups, the demographic information are more or less the same. And this including the gender, the age, and their travel purpose and frequency. So we can see overall they're quite comparable. Then we visualize the result. So on top it is the data that's collected from the 5-point scale, and on the bottom is the one from the interval value scale. And so like a few attributes you can see here, they kind of reflect quite similar trend, and which means it's kind of helpful to show our data is validated. But it's not always the same, and there are some differences. So for example, here it suggests importance of the attribute 9, which is the quality of Wi-Fi on the coach. And for the single point data, that we can say that things like most people are still would rate it as 5, which is very important. But if we look at the interval data, we kind of say their opinion is a bit more divided or kind of equally distributed among all different data points. So there's something different we can get from the interval data. And we also applied the average and interval average to get the overall summary of all these attributes in terms of the importance and the satisfaction. What we found really interesting is for the importance one, especially compared to the satisfaction, the data are very heavily skewed. So in the world, like the red circle that you can see are from the single value data, while the blue lines are from the interval data. So like for importance, we find it's really interesting in the world, like people tend to overrate the importance of different attributes when they only allow to use the single point data. And we find some support in the literature, in the way of like sometimes if you ask someone that like to rate all the importance of those attributes, they would tend towards to rate everything as important, just in case that in the world like people misunderstand it and treat something not seriously. However, it is also common from stakeholders' view. If you read everything as important, that kind of nothing is really important, because there's always limited resources and you can only doing certain things. So here we're trying to show that in the world, like we say, interval has the potential to further identify the difference between those. Because we can say some attributes for people they are absolutely important, very certain. Well, for some other attributes is, yeah, it is important, but it's kind of wibbly-wobbly and then have a range attached to it. And so in this way, we're trying to say that so for the importance, they have a skill and we may be able to identify something from them. And so we later calculated the CSI as previously introduced and also the interval value of CSI. So the result we get is, so we can say for the seat availability, which is the attribute 7, it seems just produce higher contribution compared to everything else. So for example, it's compared to the 8 and 13, which is the cleanness of the carriage and the cleanness of the toilet on the train. And so compared to those attributes, we can say for the seat availability, even in its lower bounds, is still higher than the upper bounds of the following two. So kind of it shows that people really care about this. This is giving a massive contribution compared to everything else. And another thing we identified from the interval is according to the width of it. So for example, here for the attribution level, which is self-availability, we can see not only that it has relatively lowest contribution towards overall satisfaction, but also it has the relatively lowest range too. So that's kind of showing that people are not only think it doesn't really that matter, and they also quite certain about it. Well, in comparison, there's something that gives a much wider range. For example, like the comfort waiting area, it has a quite big range. So that kind of reflects people are not really sure about themselves. Is this matter? Maybe or maybe not. So maybe something like that, we need to further investigate to say what are the reasons that cause those uncertainties. So in conclusion, we think through this pilot study that we can say not only understand their satisfaction and importance, but also the uncertainties attached to it that can help us to better understand them. And for the next step, we are thinking about further engage with the real industry to see their views and also like have a larger scale data collection. So the result, for example, like the heavy skilled data, we can get better proof from the statistics level. And thank you for listening. Any questions?
Do you have to change how you do significance testing with interval-based responses, so things like t-tests?
So far, we just basically do it as two different points. So basically, you can see the lower points is our difference, and the upper points. That's currently how we deal with it. And many other interval methods is still in development. Thank you.
Any other questions from the room? No? Okay, I have one.
Yeah.
So this method obviously gives a bit more representative results than normal. But how much more data is generated and how much more processing does it need over the normal methods?
I think there will be two stages. The first one would be like collection. In terms of collection, that we previously done different study to say that if people think this is much more heavy workload. And the overall result we're saying that is people are, after they read the instruction, they start to feel like it's quite easy to use. So it's overall people seem spend a little bit longer time to put their data, but not really much people complain about this is too complex. So I think that part is kind of more or less the same. And for another side, which is like in terms of the data analysis, I think it's more depends on what you really want to get out of it. Like if you just want to do the basic one, because all the interval value data, they can be either treated as left-right point, or they can treat as you can use the middle point. So if you want to get the basic one, they're basically quite similar. But if you want to do more things with it, there will be additional cost for the additional information you're trying to find out. But so far, we don't think that like there aren't anything that is too much in competition cost in what we're doing at the moment, because none of them is require that high level complexity.
Okay, cool.
Thank you.
We've got time for one more question if anyone has one. Yeah, on the black.
Do you see any situations to take the interval method a bit further, that the intervals can be enriched at conventional number points so they couldn't? For example, if there's a characteristic of, say there's a question where you want to consider two things, like level of comfort and level of satisfaction at the same time. I guess your method, brilliantly, could also work in 2 dimensions, so you could draw closed contours rather than just closed lines. Is this something which you might be interested in looking at in the future?
Yes, there are certainly things like that. So for example, like compared to the traditional method, there will also be the methods like progression? Yes, regression. That sort of things that is already developed for the interval value method. So instead of like we just say which elements is contribute to what, when it's increase or decrease, we're also able to say how the uncertainty of that element is have effects on the result. So for example, one thing we did previously related to customers' purchasing behavior is things like, for example, ethics. and then so ethics of the certain product and its main effects, but it's mainly through the uncertainty about ethics instead of how high the ethics itself. So that's a bit more different dimension that we can get from the interval value data. Is that answer your question?
I think so, yeah.
Thank you.
Any other questions? No? Lovely. Okay, next up we have Xiaoyu Zhen, sorry if I'm pronouncing that wrong, who has, from University College London, who has a presentation about body movement analysis.
Good afternoon, everyone. I'm Xiaoyu. I'm a first-year PhD student from UCL. Today, I'm going to introduce my work about an evaluation method for public transport environment with body movement analysis from video.
You might have to do it on the laptop if it's not working. Oh, God.
Nowadays, railway together with the underground has become a critical public transport mode for cities, but some issue has also arisen. Sometimes they may be very overcrowded, especially during the peak hours. For example, the London station's all-day arrival reached beyond 1.1 million on 2023, and for Farrington Station, there were 82,000 customers each day, and for Paddington, there are more than 100,000 customers each day. This leads to the advantage of flow analysis, which usually based on the flow speed density relationship that is quite in line with the vehicle traffic theory, but it also laid a disadvantage for the microscopic or individual analysis. But as we all know, human is different from the vehicle. We can't always treat a flow as the entirety. And at the same time, the stations are very complex. The layout and the management may vary across stations, cities, or countries. In terms of time span, they are highly affected by the large events such as sport game, concert, or the strikes. Overall, the management and design are always decided based on the main goal of ensuring efficiency. Last but not least, accident and risk still exist. In 2023 to 2024, there were 8 customer fatalities on London public transport service, and 6 of them happened in the underground. 70% of the causes of fatal serious injuries for the overall public transport system was sleep, trips, or falls, and 5% of these incidents were at the platform train interface. This fact has raised the concern of some organization and the authority, especially the Vision Zero plan that aims at eliminating the deaths and serious injuries by 2041. Okay, so the aim of the whole project is to promote a safe and seamless public transport system by optimizing the facility design and reducing pedestrian risks. The final outcome is to develop a scalable and universal analysis tool that is applicable and easily deployable across diverse scenarios and built environments. At this stage, The research targets at studying the lighting behavior through body segment movement to evaluate the impact from platform environment, thus developing an approach for safety monitor and improvement. The sub-objectives include calculating gate parameters from videos, investigating the impacts from the infrastructure and pedestrian platform, and then discussing about the applicability of this new approach. Here is the whole methodology. Currently, I'm at the preliminary result stage, but the expected outcome is to develop a new approach. At first, we took the video at Central China during work days, and the study area is a rectangle that is generally flat and horizontal. All the videos were cut into a 20-second clips for the next step. Then Alpha Post is executed for the footprint extraction. Alpha Post is a real-time multi-person post estimation system which can detect key point of a person from video, including hand, hips, knees, and feet. Here I pick the ankle point to represent the location of feet. Here we can see the demo GIF of the Alpha Post. After that, we can detect the heel strike, which is a very critical event. That means the foot contact with the ground. It was determined by the angle of knee. Once the angle reached a threshold that was determined by the biomechanical studies, we can say that the foot is located on the ground. Then is the coordinate transformation. I calculated the homogeneous metric edge based on the 4 reference points that are also the 4 corner points of the rectangle. It can determine the mathematical relationship between the pixel coordinates and the ground actual coordinates. In this way, I can get the real trajectory and the real distance on the ground. The step 5 is data processing. First of all, I excluded the data with the low confidence score. Then 3 filters were applied for the effective samples. After that, the gate parameters can be calculated, including the step length, speed, and cadence. In terms of the direction change, it was determined by the angle between vectors of 2 successive steps, like shown in the figure. In this way, we can analyze how this parameter relates with these environmental factors. At last, I got some results. In the first table, we can see that the gate parameter or the walking behavior of lighting people is quite different from the normal walking. And the box plot below show that people take larger steps while alighting from the door. It indicates that the pedestrian behavior in a station cannot be accurately modeled as a simple normal walking. In the right figure, I analyzed the distance between the door and the infrastructure on the platform. It shows that people may take shorter steps when the door they alighted from was closer to the infrastructure. It gives the suggestion that while locating the infrastructure, we should avoid locating them very directly in front of a carriage door. In terms of the direction change, we can see that people are more likely to take a smooth angle turning instead of a sharp turning, and the step length decrease with the direction change. That is consistent with previous studies. In that case, there is a need for the pedestrian to obtain a free and safe space to accelerate and turn. In the bar chart on the right, it counts the number of steps on the platform. We can see that people tend to walk near the central line and gathering in the half part. And however, at the same time, we always locate our infrastructure on the platform at the central line. So when we decide the arrangement on the platform, we should consider to decide it based on the relative flow of the two sides. In the last table, we can see that there is no significant correlation between the step length and the minimum interpersonal distance, but that is a little bit against our intuitive assumption. But the reason may be that the sample I got always maintain a large distance in front of them, and the average distance reached about 200 centimeters. In a word, based on the posture analysis using the video, I can analyze the feature of working behavior and the environment on the platform, and some suggestion could be promoted. The result is consistent with the previous studies, and thus this new approach effectively work in this particular situation, and is able to support design and management of the platform. Further, it's laid a foundation for the evaluation in the future, and it could be extended to a large scale. In terms of implications, this method could reduce the pedestrian risk and to better serve vulnerable people and the aging society. It provides insight into the bottom level of the safety pyramid. And as a cross-disciplinary research, this vision-based approach eliminates the need of a traditional wearable sensor in working analysis, and in practice, it is more cost-effective and immediate than the traditional survey or manual observation method, so it contributes to the Vision Zero plan. However, there are some limitations. The sample and the study area were limited. Larger sample is needed, and the accuracy and the applicability still remain to be validated. And that will be my that's what I will do in my future study. Yes, that's all. Thank you for listening.
Any questions from the room?
There's one here, Richard.
Oh, hello. Yeah, thanks for the presentation. In previous work, we tried here some video analysis, and we found the railway was quite difficult because it's a complicated, crowded environment. There's pillars, and people kind of get temporarily hidden and then become visible again, and that kind of thing. But that was maybe 5 years ago, and I wonder if the technology's improved. Could you tell us a little bit more about how you're detecting those people and whether you're finding that challenge of the complicated environment?
Yes. This is quite depend on how you set up the camera. If we can get a good view, the challenge will be minimized. And second is that the new algorithm, the AlphaPose, can estimate the posture of a human, even though there are some little occlusion. And last, as long as, because this is a very cheap and convenient way to collect the data, as long as we can get a long enough video or samples, even though sometimes this is too crowded, we can ignore or delete this data, and we can still get some enough data for a meaningful result. Yes. Thank you.
Any other questions?
Do you see this being possible with, for example, station CCTV cameras or staff-mounted cameras? And have you thought about potential privacy implications that customers may be concerned with?
Yes, yes, this method will be very good with the CCTV video. And during the process, we don't detect or obtain the sensitive information of people. And as long as the CCTV area has also informed people about the CCTV is working now, I think the privacy issue can be solved. Yeah.
Anyone else? No? Okay, I've got a question. So I noticed that the the videos that you had were from the tram link in London, where there's not much step between, like level-wise, between the tram and station. Have you thought about doing it somewhere where there is a step, like on a heavy rail station or a bus or something?
No, the video in the tram station is the only sample I have got now. But in the future, I can try to take more videos in other stations and with different step size or gap size, so we can analyze how people behavior change with the different environments. But now I only have this video.
Okay. One more question from me. So in the videos, it looked like the tram had quite a distance between different stopping points on the same station. So in Sheffield, most of the trams, the doors always open in pretty much the same spot. Do you think that would make it easier to design stations around different infrastructure if that was done in London?
Yes, if the train can stop at almost the same point each time, it will help us to position the infrastructure on the platform better, because like you can see the step length of the gate will change while the door they are likely from is different from the door they are likely from how close they are with the infrastructure on the platform. So if the distance is fixed, we can determine which value is the best with the relationship we can analyze. Yeah.
Any other questions, Lorraine?
Your video capturing method works well for one person, right? But if for some stations which are really busy, if there exists overlap between different people, how can it work for capture the motion for different people with overlap?
Actually, this algorithm works for multi-person estimation. Yes, and so like I mentioned before, if there are a crowd of people, the little occlusion can be accepted because the algorithm can estimate it by itself. And if we got a good view of the video or set up the cameras better, we can got a more meaningful result as well. Thank you.
Any other questions? Okay.
Thanks.
Okay, last up we have Richard Horridge from the University of Birmingham, who will be having a presentation about train positioning.
So this thing works. Does it work?
Yeah,
Is
it's
the clicky thing working as well?
Yes.
Okay. Good afternoon, everyone. As Richard said, I'm going to talk about real-time train positioning. So, first of all, the UK has big challenges in achieving the goal of accurate real-time knowledge of train positioning. And first, I want to talk about what we actually mean by real-time. Now, people that have worked with real-time embedded systems will probably cringe, but in the UK, we timetable trains to the nearest 30 seconds. So anything less than 30 seconds is real-time, as far as I'm concerned. And I'm going to go through 3 different case studies. One looking at train operations, one looking at train forecasting, and one looking at condition monitoring. And through this process, I'm going to introduce 5 different frames of reference in which we could report a train position. First, a little bit about me. So I'm a PhD researcher at the University of Birmingham, looking at next generation railway track condition monitoring. And that mainly involves fitting inertial sensors to trains and estimating track geometry. Now, my research is mainly thinking about what happens if you scale this up to potentially hundreds or thousands of vehicles, what that means and what the challenges are. And during the course of my PhD, I joined Network Rail as an operations interface manager, and there I developed tools and systems that are used by frontline operators, signals and station staff in running the railway. So the first case study is train operations, automatic or manual, routing of trains, setting routes and signal aspects. This involves a lot of decision making around the junction order, sequencing of trains at a junction, particularly in terms of perturbation and replatforming. And a lot of this is very bespoke to the signalling geography. So different signalling areas, signalers in that area have their very specific knowledge of their operational geography, and they use that in order to make those decisions. So encoding that information so that it can be used elsewhere as like a national or as a common model is very, very difficult.
And so examples would be a signalling workstation like we see there, or automated route setting systems. Next case study is probably familiar to many of us in the room. When will my train arrive? We've probably all been waiting and wondering when it will show up. Almost always the time that comes up is not always the time that it actually arrives. And it's actually quite a hard problem. It's not always easy to know where a train is, especially if it's between stations or between signals. And so we really need knowledge of speed and timings in order to do this well. This also covers the impact to other train services, conflicts at platforms and at junctions. And we're limited by the granularity and reporting of train times that is available. And so the example here is live departure boards like we see there, and traffic management systems. And the third case study, so a slightly different area of the industry traditionally, is condition monitoring. So this is understanding the state of railway track and infrastructure, which we've heard a good bit about already, like from everybody. So here we see the new measurement train as part of the fleet of vehicles that network rail used to monitor the track. And this involves positioning the vehicles or the faults in real time and historically. The typical example would be a track geometry recording trace, which is a variation in a parameter such as vertical regularity or top along the distance along the line. But there's an increasing amount of research into in-service condition monitoring, which involves fitting sensors to passenger trains or freight trains and collecting that data and comparing that. And one of the key challenges here, as Mark talked about earlier, is the alignment of one recording run to a previous recording run in order to actually make a comparison. So, where is my train? Here are the 5 different layers that I'm going to talk about in which you can report a train's position. And I'm going to try, I thought about this morning actually, I'm going to try and give an example of what a report might look like for a train at platform 2 and Sheffield Station for each of these layers. There's imagine this train's platform 1, platform 2, even Sheffield Station, get that right. So the first layer is the timetabling layer. So this is the locations of stations for timetabling purposes. If any of you have ever heard of a tip block code, this is works in this area. So for Sheffield, this would be Chef LD2, that'd be platform 2 at Sheffield. And so here you can see a visualization of the train planning system network model, which is a schematic network model linking together the locations, individual tracks and line codes. And we receive reports of trains moving in this layer via the Trust mainframe, which is a very old system and is limited in that it can only report to the nearest minute. Moving on now to the signaling layer. So for platform 2 at Sheffield, I have to double check my notes. This would be S104. And this indicates, as you can see in the diagram here, so there's a train head codes that are occupying a block section of track. We use fixed block signalling in the UK. This section of track is protected by a signal. And we have train detection systems, track head circuits and axle counters, a little bit about track circuits as well, which detect when a train has entered that section. And this layer also covers the signal aspects, route set indication, etc. And this data is output from the different signaling areas via train describers and reported up to Trust via a system called SMART. So it actually feeds up to report the times in the timetabling layer. But we can get reports in this layer to the nearest second. So next is geospatial layer, which latitude and longitude coordinates, globally understandable. We all can say, oh, okay, we know where this is. As we can see from this graphic here, unfortunately not in Sheffield, this shows points that were recorded from a train, and you can see the train clearly goes along these tracks, but the points can mean quite a lot of uncertainty associated with them. But there is a lot of volume that you can have with these measurements. So you can get quite a lot of these. And of course, there's no availability in tunnels. Next, we're on to the track map, the track centerline network model. This is a geographic information system. So if you're used to working with those, each of these is a line string. Oh, I should have mentioned, going back a second, you might report a geospatial coordinate of 53.38 degrees north, 1.46 degrees west for Sheffield. So in this network model, you might say you are a certain distance percentage along a given line string, which is a series of points in GIS. So it is surveyed in the geospatial layer, so that the geospatial layer does have a meaning here. Has some degree of uncertainty in ground truth, But the key point here is it's not directly linked with other graph network models. So we've seen the TPS model and signaling. I know lots of people here are doing work with graph models of signaling systems. It's quite difficult to go from a link between those in this network model and the network models in the other systems. And finally, onto the engineering layer. So this, of course, is a master reference for the railway, which defines how it was built, how it was designed, and it records the track lengths, traditionally in miles, yards, and chains. So see along here, again, unfortunately, lack of foresight, this isn't Sheffield, but we have mileage along the y-axis and the locations of things, including speed restrictions, other assets, etc., along there. And so this is definitely my notes for this one. For this platform at Sheffield, it would be line of route LN804, engineer's line reference TJC1, and 158 miles and 32 chains. And I'm sure the people who work with this more than me could correct me on this, but I had to double check this morning. So this again is designed in CAD and is printable. It's a digitized model, you can access it online, but the key issue for what we're talking about is it's difficult to get the semantic data out of this and then link it with other layers. And it's also, as we mentioned earlier, the basis for track geometry data reports. They're reported in a distance along a line from an origin, which is how that data on the left works. So this is a little diagram showing conversions that you can do between these layers. So here we've got the layers laid out in the diagram, and a solid line is a standard industry process. So as we mentioned earlier, you can report from the signaling layer up to the timetabling layer, which is how we get train movement reports for the most part. And you can also, there's latitude and longitude coordinates available for stations, so you get a geospatial location from a train stopping at a station. Now the dashed lines are what are described as an ad hoc process. So some of these are in use. For example, from timetabling to signaling, this is the role of a route setting subsystem. If you give it a timetable, it tells the signaling system how to route the train. Now this is quite difficult to do. You need a lot of reference data in order to do this. You need to encode that information into the model, and it's not exactly standardized or widely available, and it's generally very bespoke to the signaling deployment. So another example, what have I got? So if you have GPS coordinates in the geospatial layer, by timing those samples along with messages of indicating when a train has stepped between berths, you can understand where that is in the signaling layer. So you can link between those two layers a little bit. Going back to the example earlier we saw with the GPS points, we can use map matching, which is basically finding the nearest track line string to that point to get into the track map layer. Of course, issues there, if you have an uncertainty in that sample, it may pick the wrong line, it may pick the up line rather than the down line. So there's a lot of research into what ways to work around that. So how can we improve train operations? So then on the right highlighted are the layers in which this generally has traditionally taken place. So we're going to have fixed block signaling in this country for quite a long time, likely until at least 2050. When I was talking to Sam and the electrification people, said they want to electrify everything. Likewise, we'd love to have ETCS level 3 everywhere, but I don't think it's happening anytime soon. Though the data requirements for ETCS we're already seeing on the East Coast is there's been a lot of work on improving the quality of data and acquiring more data and making it available, which may well lead to improvements in this space. Being able to link data from signaling deployments directly with other data sources, such as the other network models, the train planning, the track center line, for example, will be quite valuable. And the key value in all of this will be improving the interfaces available to operators and giving them more data to improve decision making. For train forecasting, again, generally trains are always reported in the timetabling layer. One big thing here is GPS, and there's a lot of work being done already. Rail Delivery Group, I know, are doing a lot with this. Getting live GPS data from trains can fill in the gap between knowing like where a train actually is and when it will arrive at a location that we're reporting against in the timetable. And being able to link the other layers together, particularly the geospatial, the track center line, and the timetabling layers would allow better knowledge of distances. The distances that are reported in the reference distances between stations are almost invariably inaccurate. And if you know the speed as well, that can give you much better estimation of how long it will take a train to travel from where it is until the station. And again, collaborating across these silos to produce this joined up landscape of operational data systems, especially forecasting it's a nationwide problem. It's a big system, the railway network, and the impact of a disruption can be very large, and you need to be able to consider a lot in order to understand it. And finally, the third case study, to improve condition monitoring, again, generally we'd have reports in the engineering layer, in a distance along the track, or in the geospatial layer. Having a consistent frame of reference is key. Being able to relate all reports that we get to one another and clearly say, I know this measurement is of this particular asset, this particular fault, this particular curve, for example, is very important to be confident in the quality of the data. It's possible to bring in information from the other layers. One thing I'll be looking at over the last couple of years in my PhD will be on bringing in signalling data and linking that in, giving you more knowledge of where your train is and where it's going, which can be very useful if you're, for example, in service trains, you don't actually know where you're going, you don't know what your train's supposed to be doing. And it can also serve as a source of live GPS data to help with the other use cases. So being able to bring in GPS data for train forecasting, if you already have that because you've put sensors on trains and you're collecting that data, then you can then potentially use that to help with the forecasting problem. And allowing to relate the engineering line position to the geospatial and track map position, again, quite a difficult problem, lots of research in there. There's a lot more work to do in this space. And so, there we go. To conclude, so I've very briefly introduced three very big case studies. And the sources of position data that they all rely on do complement each other quite well. Again, it's been talked about a lot this week already. There's a big need for more integration of the data across industry silos, especially where it's not traditionally being communicated. And it may have really big benefits to network performance if we can understand more about where trains are, where they're going, how they're going to get there, how long it will take. And we could, with a lot of the data and reference issues, we could mitigate these by starting from scratch, but how likely is that to happen? It's going to cost a lot of money to dig all the track up and start again. So we're likely to have to make do with the infrastructure that we've got for potentially a very, very long time. And so that's all I've got. Are there any questions? Yes. Oh, yes, yes. Yes.
Yeah, and we are facing two kinds of problems. Firstly, didn't cover all lines in the UK.
No, it doesn't. So a lot of areas, I mean, there's the two types of data for those in the room is C-class and S-class. C-class is birth step data. So that's saying that a train has stepped past a signal. And S-class is the state of signaling infrastructure, whether it's points direction, route set, signal aspect, etc. So it's increasing in coverage. So we do get a lot of areas now have full C and S class, which means that you have all of that data available. Some areas don't output things like route set indications. So you might have signal aspects and not route set. Other areas do not output this information. And it's, again, like, I mean, I'm probably in a position where I should know. I can't honestly say for certain what the coverage is. But it is increasing. But there are some limitations in it still, in that the signal aspect data doesn't show, in the S-class feed, doesn't show the different restrictive aspects. It only shows whether a signal is red or not red, which again, for some use cases is fine, but for others, you really need to know if you're seeing a double yellow or a yellow. So does that help answer your question?
Thank you for sharing. And another question is
Sure.
about the distance between the consecutive verse is sometimes so long.
Yes.
It's hard to predict the motion because of this. How do you think about this?
Yes, no, it can be. So last year before, a long time ago, project, we were doing a project with South Western Railway looking at this in system operator, and one of the key things is having that GPS data for long berths, because berths could be 10 kilometers long, and if your train is stopped for whatever reason in the middle of that, you don't know where it is, you don't know how long it will take to get to the signal. And operators generally don't have any way of looking at that information currently. Like, operators aren't provided with a screen that shows them where their train is on a track map. So we did a proof of concept that looked at this with historic data rather than live data, but it was able to do things like identify berth boundaries, and showed real-time movements of the train. And that was with 5-second GPS granularity. I think 1 second is realistic off a train, maybe with some amount of latency. But I think the challenge really is getting access to that data. We've been trying to do that within System Operator for quite a long time now. And it's no one's really said, we're going to solve this problem, put it all there, and you can go and use it. You have to find a reason to get the data first. And then justifying that can be quite difficult. Oh, yeah, so you're in front of me, so.
Oh, okay, sorry. So I'm doing my research in ETCS level 2, and
Yes.
I wanted to ask you, because we already have a pre-existing infrastructure in place, obviously,
Yes.
and we need to retrofit the ETCS level 2 to our existing license. That's the plan of the network rail from what I've heard, rather than want to enroll level 2, or I do level 3, as you said, but that's out of the picture for now. And the question is, have you considered how we're going to combine the data? Because how are you going to use like balises, for example, to further improve the estimation of where the train currently is, and has this been considered, like how it's going to work with pre-existing infrastructure?
Yes, yeah, that's a good question. So yes, so balises are, when they're fitted, you can survey exactly where it is in the geospatial layer. You can get a mileage in the engineering layer. So it comes down to you whenever you install an asset, you should be recording this information. And then, of course, every time you detect that balise from then on, you know exactly where you are. The challenge comes if you can detect a piece of infrastructure, if you don't know where that is, and then you can't relate that to
other layers.
Another layer
Yeah.
that's relevant, yeah.
Because the problem, I guess, is like combining all of the layers together, because like you have so much data from different layers,
Yes.
and then combining it all together and finding actual right pictures, and like might be to some degree might be an actual estimation of where the train is rather than the actual position.
Yes, well, exactly. And again, I didn't really touch on this, but it is always going to be an estimation. You will always have uncertainty. So my research, my PhD research at least, is mainly looking into, at the moment, estimation of track geometry reports. And distance estimation is very difficult. And you have uncertainty with that even with the same vehicle. So you have to always account for that uncertainty. And you can use sensor fusion, I guess data fusion technique covers a lot of this stuff, to improve that estimation, as long as you know exactly the uncertainties that you're then working with. So yeah, it's always going to be an estimation. And depending on your use case, that estimation may be good enough. Like, we're still really limited by the fact that we only know a train's arrived at a station it rounds down to the minute. So it might arrive at 59 seconds past the minute, but as far as it's concerned, it's at the minute. And even just getting that to 30 seconds would be a huge improvement.
Thank you.
That's right. Mark.
Yeah, I'm just wondering how sort of the infrastructure level data works with other infrastructure managers where we share it. I'm thinking like
Yes.
my journey home from London,
Yeah.
where I might use open source data like open train times.
Yes.
I know on the Chiltern lines that when the train gets to Harrow on the Hill, it just disappears off the map. It doesn't reappear until you get to Amersham.
Yeah.
With just a message saying this train's left Harrow on the Hill.
Yeah.
And
it's interesting. I mean, it's one of the challenges we have. I've mentioned it earlier when talking about the signalling outputs, is that we haven't really got a common across the board model of the data that comes from the track. And there's a lot of talk about saying, oh well, we should just remove train detection entirely and rely on higher levels of ETCS or on GPS more. But I think there is definitely still a place for that data. You're right, it is definitely a big challenge. I think in that specific example, if you could at least get GPS data, even if you're not using it to make a decision, or an operational decision, then you can use it to give for example, a forecast decision on, okay, well, my train is now somewhere along here, and I know that it's got 5 miles or so left to run. I mean, even the distances along the track don't even need to be that, like signal box map, which we talked about earlier, that has just a line of route. And so it's very easy to map match to a line of route because it's just one line. So if you do that, that can make it a lot easier. And we see more of this happening, I think. It's just seeing that across the board, I think, is the big challenge. And it comes back to that big picture. How do we tackle this as a whole industry, rather than what it's often been, the routes are responsible for this area, so they won't upgrade their signalling here because there's no business case for it, but it does support other use cases as well.
yeah, it's just data and data availability for public use.
It's a big challenge, and as you mentioned, open train times. The operational data that I mentioned, the timetabling layer and the signalling layer data, you can get all of that freely available via the Network Rail open data feeds, and that's been available for a long time. But of course, the challenge is that, again, a colleague mentioned, is working with signalling data is very difficult, and the reference data that you need to decode that data is not very freely available. And some of it probably won't be for a long time, because signalling scheme plans, if they were all published, then people would suddenly know where there's loads of cables to go and steal. So there's a big risk to doing so. I saw a question over there earlier. Oh, hi.
Thanks for the presentation. We know that the real-time train position is very essential for the advanced railway system in the future. So, but we know position, real-time position is just a part of the railway system. It's very complex because the railway system is very complex.
Yes.
So, what do you think? What do you think about the main challenges for the real-time train positioning to achieve a collaboration?
Do you mean to achieve collaboration between the industry to achieve this? If I'm honest, I'm not too sure. It might be a good question if Paul was still here. I think a lot of the problem has always been that the accountabilities for delivering the network based on real-time position sit in a different place to the accountabilities for operating the network. So the information that we get, for example, from GPS, which could really help to inform real-time train position for a lot of use cases, that's historically just gone out to the operators rather than to Network Rail, whereas Network Rail employs the signallers who are accountable for routing trains effectively, and of course the route controllers. So I think it's potential that GBR might help solve these problems. I think it will take a long time to solve. I think the big thing is just going to be to demonstrate what is possible, that we can do more than we have already done. And I know that it's going to be a big, potentially many decades challenge in order to do this. But I'm hopeful that we'll be able to get, in 10 years' time, we'll be able to have a much better idea across the industry than we do currently. Chimeta? Sorry,
we don't have much time.
Okay. I'll grab Chimeta after.
Yeah, if you've got any more questions, please do approach them during lunch. Yeah, thank you.
Yeah, pleasure. Thank you.
So it's now a lunch break. Also, please bear in mind the closing of the presentations and posters is closing at 4. So there's not going to be much time after the next session to have another posters. So please do make sure you do that during lunch. Thank you.